background of this project, in power system, maintaining stable voltage is critical of the safe and efficient operation of electrical equipment. Voltage fluctuation due to load changes or disturbance can cause equipment damage and power supply disruption. This project aims to compare the performance of three classic controller types, which is P, proportional, PI, proportional integral, and PID, proportional integral derivative, in regulating voltage using MATLAB or simulation. So we will evaluate each controller based on rise time, overshoot percentage, settling time, and steady state error. For the first theory, first one is P controller. The equation is UT equal to KPET, where UT is the controller output, ET the error signal, and KP is the proportional gain. P controller respond proportionally to error magnitude. Its advantage are simple design and fast response. Its limitation include steady state error and potential oscillation if KP is too high. The second one is PI controller. So the PI controller which at integral action, the equation is UT equal to KPET plus KI integral ET dt. So where KI is the integral gain. The integral action eliminates steady state error by accumulating past error. This makes it suitable for application requiring high precision but may have slower transition response. The third one is PID controller, which combine all three actions. Its equation become UT equal to KPET plus KI integral ET dt plus KD DET over dt, where KD is the derivative gain. So the derivative action predicts future error trends, reducing overshoot and improving stability. PID controllers offer the best overall performance, but it's more complex to tune.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Rasyid bin KASIM, BE2040109. So in this video, I want to demonstrate the P, PI and PID controller. So this is the model that I have designed to demonstrate our project. So we have here is VIO step and PID, amplifier, transfer function, sensor, and terminal voltage in per unit, terminal voltage in kilovolt, and the base voltage. So basically we have PID here, PID component. So first of all, I want to introduce the P. So P, we press P and we set up the P1 and this I0 and D0. Okay, so we see the signal, right? Wait. So here the signal of the P, and the wait. Press here. We not run yet. Okay, we run first. And this is for the P. Okay, we wait a little bit. Yeah, that's it. From 0 and above. And then for the kilovolt, the graph is like here. And then we set up back for the I we put 1. We press apply. Okay, and we run back. No. Okay, you see the graph. Okay, nice. And then for the kilovolts, yeah, like this. And then we change the PID for the B equal to 1111. Alright, we apply and OK, and we run back. So we see the signal is like this. Yeah, good one. And this, yes. Okay, then we want to make a closed loop. We delete this and we connect, and then we run without the PID, guys. So we run. Okay, we see the graph. It's like this, and for this one it's like this. So for the, we delete this, delete, and this one also delete. So we run. Yeah, the graph is like this. This is for the open loop, guys, without the sensor and without the PID. See, yeah, right. And then for the KV, yeah, so like this. Okay, that's all from me for the demonstration. Alright, thank you. Next.
Hello, my name is FLAVIO RUTUT. My matric number is CE 230010. I will demo for frequency domain analysis and task 3 RC low pass filter. Firstly, you need to write the command, which is F equal to N times F0. Then write the main X equal to ABS. Then we write command paste equal to angle, which is angle time to 180 pi, and we write the figure name task 2 with frequency domain, then write the subplot 211 and steam F slash 1E3, then main X select title, X label frequency kilohertz, then Y label magnitude and grade on. Next is same like the before, subplot 212 steam F slash 1E3, then we write paste here and plate title and X label frequency kilohertz, then Y label paste degree grid on. Next is task 3, which is RC low pass filter. What we need to write the command is hn equal to 1 slash bracket 1 times 1 plus 1 j times f slash fc bracket. Then we write main hash equal to abs, this is sn. Then we write pass hash hash equal to angle sn times 180 pi. Then we write figure name task 3, it is filter response. Then we write subplot 211 plot bracket f slash 1 e3, then main hash magnitude hash, then write title hash f, then x label frequency kilohertz, then y label magnitude, then we write grid on, same like before. Then we subplot 212 and plot f slash 1 e3, then we write paste hash here, title hash ss, then x label frequency kilohertz, then y label paste degree breakpoint. So the result for domain analysis and task 3 RC low pass filter is like this. So this is a frequency domain for task 2. Then this is task 3 filter response. This is the graph. That's all for me.
So for the auto tune, firstly double click at the controller and select P, and then select the tune, and then OK. So this is the graph for the auto tune. So next for the parameter. Okay, this is the parameter. So next for the PI controller, choose the PI controller and then select tune. So this is the graph for the PI controller, and then the parameter. So this is the parameter for the PI controller. So next I'm gonna show for the PID controller. So this is the graph for the PID controller, and this is the parameter. Okay, that's all from me. Thank you.
Project contribution with SDG, performance comparison of open loop P, PI and PID control. This study on voltage regulation in power system directly advanced SDG 7, which is affordable and clean energy by improving the stability and efficiency of electricity delivery by reducing voltage fluctuations and minimizing losses. Optimized voltage control enables higher penetration of renewable generation, lowering greenhouse gas emissions and operational costs. Furthermore, enhanced power quality support SDG 9, which is industry, innovation, and infrastructure as more reliable grids, foster resilient industry processes, encourage technological innovation in control system, and extend electrification to underserved areas. Finally, by preventing equipment damage and reducing energy waste, effective voltage regulation contribute to SDG 13 climate action, helping utilities meet emission reduction target through smarter low carbon operation. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad ZULHILMI bin Zuhairi. My number metric is CE230112. For discussion, our project is from performance comparison of open loop P, PI and PID control. In an open loop, the amplifier and plant alone produce a smooth monotonic rise to about 10 pu, reaching 90% in 2.48 seconds and settling by 4.52 seconds, but with a huge steady state error. Final value 10 pu for a 1 pu step. Introducing proportional feedback. P 0.30 correct that offset and speed the rise to 90% in 0.51 second. Yet in use 27.1% overshoot and settles in 3.74 second. Adding integral action PI P equal to 0.20, I equal to 0.11. Threads a slower rise 0.84 second for minimal overshoot, 5.2% and 4.97 seconds settling. Finally, the full PID P equal to 0.21, I equal to 0.19, D equal to 0.057. It deliver the best overall performance. Sub 1 second rise 0.93 second, low overshoot 4.4%, and the quickest settling 3.33 second, while also maximizing robustness margin. In conclusion, this comprehensive study on PID controller tuning method specifically applied to voltage regulator power system has successfully achieved its primary objective, which include evaluating the effectiveness of the Ziegler-Nichols method and the PID auto-tuning technique in optimizing control system performance across various voltage regulation scenarios. By systematically measuring key performance indicators such as response time, overshoot, steady state error, and overall stability, we provide a true comparison of these two widely used methodologies, thereby contributing valuable insight to the field of power system control engineering.